very negligible force when you are designing for a small load. But torsion is a major factor. From now you note that the structure cross section will get reduced. Ground floor you will be having one cross section, and Empire State Building, this is the example of that. Burj Khalifa is an example of that. Whatever facility you are having in the ground floor, which will be slowly reduced when you are going into the top. In a steel structure for large applications, you can see buildings, residential buildings are constructed by using RCC only. This is of small scale. But if you need to construct a bridge, can you see purely concrete bridge, a large scale bridge? You cannot see only concrete. You can only see steel oriented bridges. If you need a mobile tower, have you seen any RCC mobile tower? You will be not seeing that. Why? Because there is a reason that steel, the behavior is purely elastic. In concrete, there are two different materials. One is steel and another one is concrete. Concrete is best for taking compression load. Steel is best for taking tensile load. So when you are making a column, you will be having both concrete and steel. From the slab, it gets transferred to the beam. Who is transmitting? Either steel or concrete. Steel is transmitting. When you are designing for a compression member, the last module, what you have done? If a member has to carry a compressive load of 1000 kilonewton, if you apply 1000 kilonewton, the member capacity might be around 700 kilonewton. But if you are making a tension member, this member can carry whole 1000 kilonewton. If you are designing the same element for a compression member, this carries less load. The same member, if you are using it as a tension member, it carries 100% of load. Why? Because it takes all the tensile force equally. Can you see that you have done a UTM test? In that you will be placing a steel member. How you have tested that steel member? Either you have tensioned or compression. You have tensioned. Note that when you are finding the behavior or material of the member, you are tensioning. Why? Because when tension, you will be knowing the pure yield capacity. You can do the same test by using compression. In a UTM machine, you can also compress. Why? Because the material will not take the 100% yield load before the failure. That is why the tension test is being done for finding the load carrying capacity of the member. The structural element that are subjected to direct axial tensile load that tend to elongate. Whatever you are using as a tension member, let me come from here. This is a cable stayed bridge. What do you mean by cable stayed is you will be having a pier. One and only two number of piers will be here. By this you will be having cables. These are all known as cables. All the cables will be in steel only. Okay. Now by using these cables you will be having a flat element. This is slab. From the slab all the loads will be transferring. Either car, automobile, whatever might be the automobile. The load whatever is here which is being carried by cables. Always the cable is subjected to tension only. If you are keep on adding the load here, what will happen? You get tension only. But what will be the behavior of this pier? If you are increasing the load, what will happen? This member always compresses. Find the difference. In a single bridge, you are having two members. What are they? One is compression member, one is tension member. What is a compression member? A pier is a compression member. If you are increasing 100 number of cars, what will happen? The cable will always get tensioned. The pier will always get compression. So, in a complete set of members, you will be having both compression and tension member. In a bridge, you will be having two number of elements. So, this is the element which you are going to discuss now. The last module, whatever you have studied, which is used to design the piers only. Not only in the cable stayed bridge, you have the next example of a truss. So, this is a truss. Imagine that this is a warehouse. You are having a truss members. These individual members are called ties. The ties will be having both compression and tension. What is the method of analysis to find the forces in a truss? Method of joint, method of section, method of tension coefficient. These three methods are there. So method of joint is used. You will be finding all the members. Whatever the ties, how much is the force acting, you will be knowing this. In the ties, always the bottom chord. This is known as the bottom chord. This bottom chord always tends to tension. Imagine that you are having a truss member. If you are keep on adding the load, what will happen? The bottom member tries to tension. So this is the example for tension members. And in bracings, you will be having ties. Have you seen these bracings? Bracings are the members which is provided to take lateral loads. This is a tie. This is a large building. They have constructed the building by using this technique only. Hanger bars. You will be having a hanger bars. There is a long column and you will be having a tie. It will be suspended. All the ties will be suspended. So this member is called a suspension member, and in suspension bridge you will be having the cables. All the cables are section only. If you keep on adding the load, cables will get elongated. So this is the understanding. Okay. The member is in pure tension. You will be not having any other force. What are the four types of force? Axial force, bending force, shear and torsion. In a tension member, you will be having only tension, that is axial force. In axial force, you have two components, axial tension, axial compression. So you will be having purely axial tension in this member. It can be stressed up to beyond the yield limit and does not buckle locally. So there is no point of buckling in the tension members, and the design is not affected by section classification. In design of compression member, while starting I have discussed with you the types of section. So what are the section for the steel structure? Plastic section, semi-compact section, compact section. These three are the types of section which is there in your code book also. You have a tabular column, you will be selecting breadth to thickness value in order to find that. Okay. The tension members carry load most efficiently when subjected to uniform stress. Note that how you have to design your members. Your members should be having uniform stresses. If you are making this as a tension member, to connect the bolt only at this center in order to get most efficiency. And the connection size, spacing of fasteners, net cross sectional area, type of fabrication, connecting with eccentricity and shear lag. These components will get affected. If you change the size, spacing of fasteners, the strength gets affected. So these are the factors which affects the strength of the tension member. The member also becomes non-functional due to excessive elongation. So this I will discuss with you in further slides. Where are the tension members available? In bridges, transmission lines. It might be electrical transmission line and communication towers, wind bracing system in multi-story building, etc. So these are the example. And in suspension bridges, so this is called suspension bridge, and this is called cable stay bridge. Find the difference between that. This is called suspension bridges. Suspension bridge is acting upon only one parameter, that is called suspension cable. Only one large member will be there. This is a continuous member till the end, and all the cables will be coming from this main cable. This is called suspenders. Suspenders will be hanged with the main cable. But in terms of cable stayed bridges, all the cables are being connected with the piers. But here it is not directly connected with the piers. It is connected with what? Main cable. So this is the difference. In suspension bridges, the suspenders are connected with the cables. In cable stay bridges, it is directly connected to piers. So this is the difference. Now slenderness ratio. The ratio between unsupported length to the least radius of variation. This is known as slenderness ratio, that is L by R. When you are designing the tension member, you should check that this comes below the maximum effective slenderness ratio, that is KL by R. Table number 3 in IS 800. A member which is carrying compressive load resulting in dead load and live load, what is the maximum slenderness ratio? L by R is 180. If you are designing a tension member, the maximum slenderness ratio should be 180. Also you have compression flange. This is a compression member. Members are always under tension. Other than pre-tension members should not go beyond more than 400 mm. So this is used for cable stay bridges. The last component. Members are always under tension. See, some member might be tension for some period of time and it might be compression for some period of time. Why? Because in a sloped roof, wind might be blowing at one side and the leadward side will be under a tension. So, if wind is blowing at another side, it gets changed. Your member is loading, the member can either be tension or compression. But certain members are purely tension, whatever might be the load. So, that is the example of this. Members always under tension, it should be 400. Members might be reversal, the load might be reversal. In those cases, it should not go beyond 180 mm. Okay, what is the use of checking slenderness ratio is, it prevents the lateral movement and excessive vibration. How a tension member can fail? When you are designing, you should know the failure criteria first in order to design. That is why in design of steel structure, what are the contents there in module 1? Plastic collapse. Before doing any design, you should study the collapse mechanism. How the material fails. The same thing which happens practically. If you want to ride a bicycle, you should have fallen 100 times. Everybody would have fallen, yes or no? Without falling, can you learn the cycling? Not possible, practically. Without sinking inside the water, can you learn swimming? First time I will fall into a well, I will not at all sink. I will learn swimming. How come it is possible? It is not at all possible. So if you want to swing the stick, there is a skill. If you are training that, definitely in the head, in your arms, without getting a single hit, you cannot train with that. So if you want to design or if you want to learn certain things, first you should know the failure mechanism. How the member can fail, how the tension member can fail. First mode of failure is gross yielding. So this is the title here. What do you mean by gross yielding is, take an example, this as the tension member. If I am tensioning this member, it will fail in between the member. So this is one connection and this is another connection. If I am tensioning this, it will fail in between the member. So this is being yielded in the member, called gross yielding. How to overcome that? TDG. What do you mean by that? Design gross tension. T stands for tension, D stands for design, G stands for gross. So your gross design tension should be equal to 0.909 FY/Ag. This is a member. Can you see this member? The cross section is reduced at the center. This is one mode of failure, cross section yielding. So this cross section will get reduced. You can see in tension test when you are doing that. Have you seen the neck formation? Second one is net section rupture. A tension member which is having the holes, wherever you have connection, at those points you will be having what kind of failure? Net section rupture. But what is gross yielding? It will not occur at the joint. It will occur at midpoints. In a bolted connection, you can see that if member is failed, can you see the hole is being increased? Hole size is being increased and you have the rupture here. This is called net section rupture. Why? Because this is the total area, this is the net area. After reducing the two holes diameter, you will be getting the net area. So when a failure occurs along this plane, it is called net section rupture. And you can see that when you tension any member, there will be equal number of stress in the two sides. But wherever you find the holes here, there will be less stresses. This is the hole and you can see that there is a sudden drop of stress. So due to that, we are having the failure. Third type of failure is block shear failure. The mode of failure where majority of the steel structure fails. Can you see this connection? So this is a gusset plate and in a gusset plate a member is being connected and you have 8 number of bolt. If the force is large, what happens? There is a area which is the line which is given here, 1, 2, 3, 4. So this is the area. If you are tensioning this member, this area, the tension force will be maximum, 1, 2, 3, 4. These are the areas where you have maximum tensile force. So what happens if you pull this object, the force which is acting along this object will be tensioned and the member gets failed in this area. So this is called block shear. As a block, it is getting shear. So this is known as block shear. The failure can happen like this also. This is for plate and this is for angle section. Angle section means what? L section. If you are providing L section, the failure might be in this pattern, and if you are providing plates, this failure might be in this pattern. So here it says that the path involving the tension on one plane and shear on perpendicular plane along the fasteners as shown in figure. 6.4.1 bolted connection. Page number 33. How to find the design block shear strength TDB. They have given the two formulas. Either of the formula you can use. For the same thing in IS 800, they have given formula for gross yielding and the formula for rupture for plates. 6.3 is for plates. Do you have critical rupture for angle? 0.3.2. You have separate formula for that. All the formulas given in your code book. There are three types of failure in tension members. For all the three types of failure, you have formula in the code book. The angle section will fail like this. So this is the line of action. So the force act along this line. So the failure occurs like this. The plane 1, 2, 2, 2. Okay. This is an example for the gusset plate failure. This type of failure is called block failure. This phenomena is possible mode of failure when bearing strength and the bolt strength are much higher. If your plate strength is also high, it will not fail. The bolt also is very much higher strength. The only one way of failing is called this block shear failure, which will happen in this connecting member. Okay. So this is the final understanding of that. If you are having two plates which has been connected by bolt, if you are tensioning this member, gross yielding. It is not acting at the joint, it is acting in the member at any section. This is called gross yielding. Net section rupture. Why? Because the rupture is between the bolt holes, you are having this rupture, hence it is called net shear rupture. It might be like this or it might be like this. You can see the connection. At the end of the connection, the failure occurs. Block shear failure. And this is block shear failure for plates. If you are providing angle section, this angle member, your block shear will be in this mode. Okay. Factors affecting the strength of tension member. First one, effect of bolt holes. If you have more number of holes in your plate, then it reduces the tension carrying capacity of this member. If holes are high, tension carrying capacity gets reduced. Then next is method of fabrication. How you fabricate your member. This second case. Then effect of shear lag. What do you mean by shear lag is, if any angle member is connected like this, in the angle section you will be connecting at one leg only. This is two leg. This is leg number 1 and this is leg number 2. You will be connecting at one side only. The other side you will be not having any force. One part you are connecting with the member, other part is free. So there is a force difference between these two leg 1 and leg 2. So there will be lagging of force. So this force lagging is called shear lagging. Next thing is geometry factor. If your section is symmetrical, your load carrying capacity will be equal. Next factor is ductility, spacing of fasteners. If you change any one of the factor, the strength of the member gets increased or decreased. Let us take the first problem. Determine the tensile strength of the plate. You have plate number 1 of size 130 mm by 12 mm. This is width of the plate 130 mm and the thickness is 12 mm. Okay. With the holes of 16 mm diameter bolt. So they have given only the diameter of bolt. Then what will be the diameter of hole? 18, 16 plus 2. That is 18 mm diameter of the hole. As shown in figure, steel is used of Fe410 grade quality. Ultimate strength of steel. Design strength due to yielding of gross section, that is TDG. Rupture strength of critical section TDN and block shear. you have edge distance between the end of the plate to the extreme bolt. This is 35, and here also you are having 35. Pitch distance is 60, gauge distance is also 60. Now, first design strength due to gross yielding, TDG. TDG equal to AG Fy divided by gamma MO. What is AG? Gross cross section area of the plate 130. What is the thickness of the plate? 12. If you multiply, you will be getting gross area. What is Fy? Yield strength. They have given the yield strength, and gamma MO, you know that 1.1. Note that this is Fu. Fy is for 410 grade steel, you will be having 250. Fy is 250, gamma MO is 1.1. You have this class 6.2, 1560 into 250 divided by 1.1. 354545 Newton. That is 354 kilonewton. Fy is yield strength or yield stress. What is Fu? Ultimate strength. When you are substituting here, note that what is Fy. Do not confuse with that. Rupture strength. Here you have the formula 0.9 An Fu divided by gamma M1. Class 6.3. You have this formula. An net effective area of the member. What is net effective area? See, you have gross area. After providing two holes, what will happen? Area gets reduced. So, how many holes are here? If you are substituting 130 minus 2 number of holes, diameter of the hole 18. 16 plus 2 is 18. This is your net width. Width into depth will give you the net area. What is gross area is? Without considering the holes. What is net area? After subtracting the holes diameter, then the area is known as net area. I have the formula here. Now you know the An. What is Fu? 410. They have given in data. And what is gamma ML? That is partial factor for failure at ultimate stress. 1.25. Yes, you can see that. Resistance governed by yielding gamma MO, which is 1.1, table 5, and resistance governed by ultimate stress. So here you are taking ultimate stress. When considering ultimate stress, you should take gamma ML, and it is 1.25. Hence, if you substitute this 1.25, what is your answer? 332.986 kilonewton. Now, third thing is block shear strength. AVG is minimum gross and net area. AVG is gross area and AVN is net area. What do you mean by that? Along the bolt parallel line to external respectively 1, 2, 3, 4 as shown in figure 7a. So, this is 1, 2, 3, 4. So, this is the area. This is 1 and this is 2. What is the distance? 35. This distance is 35, and next from 1 to 2 is 60, and you have two lines here. So, I am multiplying it by 2. 35 plus 60 into 2, thickness 12. I will be getting 2280 mm square. This is AVG. That is minimum gross area in shear alonging 1, 2, 3, 4. So, this is 1, 2 and this is 3, 4. ATG is minimum gross and net tension area from bolt hole to the toe of the angle in bolt line perpendicular to the line force respectively to 2 to 3. So, what is 2 to 3? 2 to 3, what is the distance? 60. So, 60 into what is the thickness? 12. This is ATG. 720. What is AVN and ATN is net. This is gross area. What is net area in the sense? You have to subtract diameter of the hole. You have two holes in this line. You have two number of holes, hence you will be subtracting 35 plus 60 is the total distance. How many holes are here? 1.5 holes. How 1.5 holes is? This is full hole which is covered, and the line of action is only up to the center. From the center it takes the direction in the right hand side. So 1.5. So 1.5 into 18 into 12 into 2. Why they have multiplied into 2? You have two parallel lines. Now your area is 1632 mm square. The same way along this direction, your net area from the center to the center, you have to subtract only 18, that is 0.5 and 0.5 there, half of the holes. It will be one pure hole. 60 minus the same thing, whatever you have written here, subtract minus 18. Why? Because the line of action is only through the centroid. So after the centroid is not considered. In this direction also, after the centroid you have half hole and you have another half hole. So half plus half is 1. So you are substituting one pure hole. What is the one pure hole is 18 mm. ATN. Now in this formula you can substitute what is ABG. You have all the values. Fy is 250, root 3, gamma MO is 1.1, 0.9, ATN is 504, Fu is 410 divided by gamma M1, which is 1.25. All the values are known for you. You have got all 4 answers. The second answer, what you got is 441 for this, and at first answer you will be getting 2280 and 504. Okay, what is the least of that? 332 is the least. So the strength of the plate is considered as 332.98 kilonewton.